Okay, today we're going to get started on section 5.3. 5.3 deals with the average value of functions. So far we've been looking at functions and their area underneath the curve, using the integral to find that. Today we're going to use our integrals to find the average value of a function. And so we have a little bit different equation to find that average value. So if we have this function here, f of x, on a closed interval from a to b, what we have to do to find, so here we have the average value. To find the average value, we take the integral of that total area underneath the curve from a to b, so f of x dx, and we divide it by that change in our x's, so b minus a. Oops. And that's going to give us the average value. And we rewrite this a little bit differently. The average value, what we do is we take that 1 over, we take that 1 over b minus a, value. We take this b minus a and write it as 1 over b minus a times the integral from a to b of f of x dx. So this is that formula we're going to use for average value, to find the average value of a function on a closed interval. That's what they're going to give us. So in semester 1 we talked about the average velocity of a function. And we said that the average velocity of a function was given by the equation s of b minus s of a over b minus a. So that's our change in position over the change in our time. But now we can use the fundamental theorem of calculus to show that the average value of velocity is actually that. We can prove it using FTC, what we did yesterday. And it's pretty simple, actually. What we do is we start with our integral here from a to b of our velocity, and we're saying that if this is true, by the fundamental theorem, we have this equal to s of b minus s of a. So our change in position is equal to the integral of the rate of change. Okay. And again, what we can do now to both sides is we can multiply by 1 over b minus a. So we end up with 1 over b minus a of the integral from a to b of v of t dt equals, think of it as 1 over b minus a times s of b minus s of a. And just so it looks the same as this equation up here, we can rewrite that right side of our equals as s of b, oops, let's go lowercase b here, s of b minus s of a over b minus a. Okay, so again, just proving that what we said about the average velocity of a function was true using the fundamental theorem of calculus. So here we get into an example, and it says, suppose C of t is the daily cost of heating your house in dollars a day, where t equals 0 on January 1st, 2005, not 1995, 2005. So state the meaning of the following integrals, including the units. So this is what we worked on yesterday here. The integral from 0 to 90 of C of t dt. So C of t, our units are dollars per day, and we can think of d of t as being the same thing as days, so kind of like our change in t's there. What ends up happening then is our days cancel out, and our final answer is going to be just in terms of dollars. Okay, and if we use this with our example, it's not just dollars, it's the total cost of heating your house, or total cost to heat your house for 90 days. And we can say more specifically for January, February, and March. All right. Next part here, we have to interpret this, see what it means. First off, let's look at the units. So 1 over 90 is 1 over the days. And we already said the value of this integral here was in terms of dollars. So our units are going to end up being dollars per day. So what that problem right there is saying, what is the average cost to heat your house, average cost in dollars per day to heat the house. So the average cost in dollars a day to heat the house. Next one here, we have this function says P, or f of t, equals 67.38 times 1.026 to the t power. And it says P is the population in Mexico in millions, and t is years, where t equals 0 means 1980. And they want us to find the average population in Mexico from 2000 to 2020. So average value, our form is 1 over b minus a times the integral from a to b of our function f of x dx. So in this case, our b value, since this is in 2020 and we're supposed to start in 1980, our b value is going to be 40. So we have 1 over 40 minus 20. So we end up with 20 here and 40 for our integral. And this function we have is back up top here, 67.38 times 1.026 to the t power. And can't forget our dt. Now, we don't know how to evaluate this integral yet, so we can use our calculator to do it. And if we go through, if we go to our calculator, so we're going to go to Math 9, and my form is a little bit different than yours, but it's from 20 to 40, and that function is 67.38 times 1.026 to the x power, and this is our, this new format messes me up, dx. So we're evaluating this integral again. If you have the fn int, I'll type in what it should look like, but let's drag the answer over here so we have that. If you're using fn int when you type this in, what you should have is fn int, your function, comma x, comma 20, comma 40. And that should give you the answer, which we just found to be, or not the answer, excuse me, the value for our integral. So if we bring this down here, we end up with 1 over 20 times 2,942.66. And 1 over 20 times 2,942.66 is 147.12, or excuse me, 13 million people. 13. And this is in terms of millions of people. All right, and the last one. We want to find the average value of this function. So that's what this is saying. The average value of our function from 1 to 6. Okay. Our equation for average value, let me scroll down here a little bit. Equation for average value is again 1 over b minus a. And our integral from a to b of f of x dx. In this case, our b value is 6 and our a value is 1, so we can plug those in here. So 1 over 6 minus 1. Now, the value of that integral is the area underneath the curve. So we need to add up the area of this function here. We've got 1, 2, 3, 4, 5, 6, 7. These two add up to be 8 and 8.5. So the area under the curve for that function is 8.5. So we end up with 1/5 times 8.5, which gives us for a final answer 1.7. So that is the average value of that curve from 1 to 6. And that's it. Here's your homework for section 5.3, finishing this up as we move into 5.4 for the rest of the chapter.